What does it mean to be an Ascendant?
It means doing things by any means necessary.
Even in the face of adversity.
From within to push away my fear, to stand where I'm afraid. I am through with it.
It means rising up to the challenge
in pursuit of greatness.
Will you be a witness?
This is how we're going to space.
The night.
They are the Rensselaer Rocket Society, and their rocket's name is the East Coast Ghost. The East Coast Ghost is a white rocket trimmed with black, and we're sending Rensselaer Polytech in 5, 4, 3, 2, 1, ignition.
I mean, the stream now, they should be able to hear us.
All right. Hello, everybody. Thank you so much for coming out on this lovely rainy Saturday. And thank you to everybody online who's showing up on our stream. Before we begin our actual presentation, we'll do a brief introduction of our team.
I'm Noah Miranda. I'm the co-founder of the Ascendant Research Group, and I will also serve as the former project architect.
I'm Lucas Long, also co-founder and the former integration director.
My name is Caitlin Morgan. I'm also a co-founder, and I'm the current project and group lead of the Ascendant Research Group.
My name is Rowan Jordan. I am the current integration director for Project Ascendant, and I'm also heavily involved in the promotion.
I'm Constantine Childs, and I'm the former chief engineer.
Hello, my name is Ella Wu. I'm the current chief engineer and mission architect.
My name is Trey Penman. I'm in charge of the additive engineering and avionics for this project.
My name is Sawyer Shaw, and I'm the propulsion and integration engineer.
I'm Joe Franciamori, and I'm the structures and dynamics engineer.
Hello everyone, my name is John Pranacchia. I'm a member of the structures team with a focus on composites and manufacturing.
Good afternoon everyone, my name is Gray Chen and I am the recovery engineer for this project.
Alrighty, so we'll kick things off. We have a little brief introduction into our team structure and a little bit about what we're actually trying to accomplish here. And from there, we'll delve into more of the technical aspects of our subsystems. And from there, we will thank all of our amazing sponsors and help that we've received along the way. And we will talk about our future plans, future work, and then we'll do a little Q&A session at the end. So I ask that you please hold your questions until then. So starting off, what do we do? So we are the Ascendant Research Group. We are a faction of the Rensselaer Rocket Society, and our mission started all the way back in 2022 is to develop a two-stage rocket on our own composite rocket propellant to launch up beyond the Kármán line, which is the international line dividing Earth and space. So how will we get there? To start off, our design is a little different from some other typical college teams that you will see. First of all, we are going with a two-stage design, which is more efficient in terms of propellant and cost than a typical single stage. Additionally, we manufacture and design our own custom propellants in-house. This is a little different from some other teams that may get them outsourced or just bought commercially. This way, we can customize our propellants exactly to our own needs. And then lastly, as you saw, we are a pretty small team. When you see rocket teams, typically they're upwards of like 60, 70, if not way more people. Our team, we like to keep it small, and all of our teammates are very highly focused and dedicated to the project, so we all have a lot of skin in the game. So I'll do a little brief subsystem introduction. We have our propulsion team. This is the one that I'm personally a part of. And we go into the actual development and formulation of our solid composite rocket propellant. This involves writing our formulas, writing our mix procedures, actually mixing the chemicals, getting all the safety procedures written out so that we can actually pull this thing off, and more. The structures and dynamics team, they design and fabricate parts for the actual launch vehicle. So our rocket, as you may be able to see up front, this is one of our stages, was all developed with CAD first and foremost. Our computer-aided design, we have full CAD drawings and designs of everything. That was all done by our structures team. Dynamics also simulates everything so that we can predict how it's going to behave in our flight. We also, sorry, one more thing. We manufacture a lot of our composites in-house. So this nose cone, fully manufactured in-house with fiberglass, but the others will get more into that later. Our last two subsystems, we have recovery and avionics. This ensures that our rocket can come back safely. Another thing that's unique about our team is we intend to fully recover both our booster and our sustainer stage. So this requires a lot of work on the teams of avionics and flight computers and parachutes to make sure that everything's coming down safely to fulfill all FAA guidelines. And additionally, as a part of this team, we have our payload, which is our camera system. And this will be discussed in a lot more detail later on, but we intend to get very high quality footage of what's going on up in space. So that's what this subsystem goes over. And then we also have our testing and integration team. Much like the name indicates, this team oversees a lot of our testing procedures for many subsystems. It works with all of the sub-teams and helps us really integrate the entire thing together and make sure that everything's kind of working properly. So, hand it over to them.
Before we get into some of the more technical details, who are we? What does our journey look like? We'll show you right now. So, the group somewhat officially began in fall 2022 in my garage, where we started mixing very low-grade sugar propellants. They're not as dangerous. They're almost inert. They're really hard to ignite, actually. And we mix these because our insurance agency, Tripoli, only allows you to do this once you're a level 2 certification, which takes a few flights, a few tests, and proof you're able to handle energetic materials. So while we were working on these certifications, we were in my garage off campus mixing sugar propellant to make sure we could get down safe procedures and talking to people who actually mix professionally propellant. Next, in winter 2022 / beginning of 2023, we made our first sugar motor launch, and it took a few attempts because, again, it's almost inert. It's really hard to ignite, and we finally got our L2s around that time. By fall 2023, thanks to Professor Oschlager, we actually acquired a lab. We started mixing high-grade propellants, and we launched a rocket to 45,000 feet. Next, in winter and spring 2024, we launched our first large-scale motor, which had 16 kilonewton seconds, and we appeared on 3 news stations and also entered the largest college rocket competition in the world. By summer, fall 2024, we competed in this competition and we actually placed second. And this also served as a test bed for our second stage of our rocket. So if you can see in your bottom right, that's the photo of our rocket that got second. And it's basically a subscale design of what the big real space shot version is going to look like. Here's some pictures from our journey. Next, I'll pass it to Joe and Noah, who will talk about dynamics.
So before you begin designing any launch vehicle, it's important to understand fundamentally the mission and the flight profile so that you can design the more intricate parts such as the fins, recovery methods, and so forth.
So over here, we have essentially a concept of operations that outlines every significant step that Joe is going to go over. Over here, you start your rocket as essentially 2 rockets on top of one another. That's essentially how the 2-stage rocket design works. Your booster stage, or your first stage, ignites at launch up to a certain point, which is known as burnout. So after that booster motor burns out, drag, the differential in the drag between the booster and the sustainer will cause them to separate. After separation, the booster would still proceed on a nominal trajectory and then deploying its parachute. In that process, the sustainer will continue coasting for about 8 seconds until ignition. That number was chosen to optimize our altitude while reducing potential maximum aerodynamic pressure. And like we show in the graph, the sustainer actually has a dual deployment mechanism as to avoid drift. This is also incorporated in the booster. However, that will be covered in the recovery section of this presentation.
So now for the actual flight profile, based off of simulations, which are semi-empirical, based off of data recovered from 20, 30 years of flight testing, early flight testing in the days of NACA, when sounding rockets were really taking off in terms of the technology that was viable. We are the simulations predict somewhere around 368, 369,000 feet. So there's a significant gap between the Kármán line and the actual altitude so that we can almost confirm that we have indeed reached space. And if our rocket, once it's manufactured, doesn't behave as we expect, which is somewhat likely because we can only produce a vehicle with such the tolerance that we have access to. We expect an apogee at around 170 seconds into flight. When the booster and sustainer stages are stacked on top of each other, we are going to reach just under Mach 2. And this Mach 2 is actually one of the, exerts a lot of force on the rocket because we're still relatively low in the atmosphere. Even though we will be expecting Mach 5 flight with only the sustainer, a lot of the aeroelastic considerations, which I'll discuss in a moment, had to be made around this low altitude Mach 2 flight. Now on the top left, we have the velocity as a function of time. Right around the time we actually do reach Mach 5, which is only the sustainer, we're a little under a mile per second in terms of true airspeed. On the right, we have the altitude, so right around 170 seconds, you can see we peak just under 400,000 feet, and then the slow descent. And the Mach number chart actually very clearly shows some of the events, some of the separation events. The very first vertically upward line is when we reach Mach 2 with the booster. It's eventually going to separate. It will coast, so we'll have a bit of a reduction in our Mach number. The sustainer will ignite once more, reach right around Mach 5, and then it's going to continue to coast until it reaches apogee. Now, in terms of the aerodynamic layout, the full stack will appear something like this. The actual sustainer stage that we will be using is right on the table in front of you. It has a 6-inch to 4-inch diameter reduction, so as a result of the needs of the propulsion team, the structures and aerodynamic considerations had to be made around this design. Of course, both stages are going to need fins for passive stability. The fins that are going to be used on the sustainer are a diamond airfoil shape with a constant thickness to chord ratio. And as a result, we are actually we were able to use some empirical data to ensure that the flutter speed would be high enough to the point where we don't have to worry about significant aeroelastic effects. And they are also beveled on the front, or they are slightly rounded on the front to reduce aerodynamic heating. Now, as for the booster fins, these had to be a lot more rigid in terms of their aeroelastic effects because they're much larger because we need stability in the full stack. And so they could be more susceptible to flutter, which is why we selected a clipped delta shape because it's more aeroelastic, or more rigid and for air elasticity, and so we can ensure vehicle reliability. And aerothermals get very interesting once we start reaching high Mach numbers. If some of you have taken compressible flows before, you know that it's a very nonlinear regime in terms of heating and the temperatures that we can expect. I used numerical data from several papers. This is an example. From here, I was able to calculate stagnation point heating and heating along the nose cone, in addition to skin friction coefficients, so that we could determine the forces that our nose cone will be experiencing. One of the most concerning being the point when we almost reach Mach 5, because as we'll see in the next slide, the heating can get quite extreme. As a result of these studies that have been conducted by others in the industry, we were able to determine that we need at least 4 inches of titanium on the nose cone. That nose cone up there has an aluminum section, but it'll look very similar in shape. And the actual tip will be as sharp as possible. The heating will be extreme, which is why we're using titanium, but we want to make sure that the frontal shock wave remains as attached as possible to reduce wave drag and hopefully increase our altitude. And to additionally protect the nose cone, we are going to have ablative materials to reduce the heat transfer. And to get a better picture of the heating, I ran a supercomputer simulation on 300 processors with full real gas effects. I assumed a 1/16th inch nose radius with a 700 Kelvin wall temperature, just for an initial look at what the heating could be. We were getting about 360 watts per square centimeter at the stagnation point, but it very quickly decreased. The graph on the left, or on the right, is truncated in terms of the y-axis, just to make that clear. It does not go to 0, unfortunately. That would make our jobs a lot easier. And on the bottom left here, that is the rounded, idealized nose cone tip. You can see that the shock wave is, it's generally less than a millimeter in terms of its displacement distance, and the temperatures we could expect are right around 1200 degrees Kelvin.
A very interesting phenomena that occurs when you're going at such high Mach numbers, and especially in thinner areas in a rarefied regime, you encounter what's known as pitch roll coupling, a lot of people call coning. Essentially, your pitch and roll moments essentially they become the dominant moments within the rocket and cause your rocket to essentially corkscrew. We have created our own in-house solver that solves a set of 11 differential equations to kind of see this effect in any sort of perturbations. So the 4 plots that are most significant here are derived from our Euler angle rates and rate derivatives, or angular velocity and angular acceleration. And one thing of note that you can see is this jittering effect, especially in our yaw and pitch. That is where you would have a lot of your coning effects, a lot of your nutations, and obviously that's an issue that we had to mitigate with our larger fins. One thing that may be asked is, why not go to a more active control scenario? It's just very hard to implement, we'll just put it that way. You're essentially making a missile. Modeling this at lower altitudes can allow us to identify failures, potential failures that can create any instances of coning, which, like I mentioned, at mild cases, you reduce your altitude by about half. In severe cases, you lose your vehicle. So this sort of modeling is extremely important, just so we can see that our geometry is validated.
And just to add to that a little bit, with this software that I coded, that simultaneously solves 11 differential equations, we were able to predict what kind of fin area we would need based off of some empirical evidence, some curve fitting, and some basic hypersonic laws of the rarefied regime. Because once you reach hypersonic, air molecules don't act necessarily as a continuum, especially at a higher altitude. They're more like shotgun pellets in terms of their behavior because they really don't mutually interact with one another. So as a result of these simulations, to prevent coding and to ensure that any resonances between the natural frequencies of your roll and pitch aren't coupled, or aren't as strongly coupled, we are able to properly size these fins and their cross-sectional geometry.
So, moving on to what happens to the sustainer once it reaches apogee and where is it going to land? Well, when launching any sort of rocket that goes beyond a certain impulse limit, this is what's known as a Class 3 rocket, you have to file a waiver and you have to file a Class 3 form. And one of the major considerations is the dispersion of your second stage, since that is most likely to drift. So we conducted a 6DOF dispersion analysis using OpenRocket. I'm sure those in the rocketry community are very familiar with the software, where we plotted the upper stage. We did 10 simulation runs. We had some issues plotting more than that due to the solver, but it kind of gave us a good understanding of where the rocket would land given 5-mile-per-hour easterly winds with a 5-mile-per-hour deviation. Our pad is assumed to be straight vertical with a 1-degree deviation. And as you can see on the chart, 90% of our landing sites are within that 15 nautical mile radius that is given by the FAA. Outside of that, essentially is a bit of an iffy area. This waiver essentially allows us to fly within that zone, but the rules kind of get a little bit wishy-washy when you have to recover outside of it. So you want to get to prove to the FAA, hey, we're going to land within the cylinder, and that's what this simulation achieved.
And now we're going to pass it to Sawyer and Rowan to talk about the development of our propulsion systems.
All right. Propulsion. What I would consider to be pretty much the lifeblood of the rocket. You can't really get to space without it. So, what is the goal? Provide the means to get to space. You need to be able to actually have something that powers your rocket in order to get into space. So, what does it need to do that? We have to utilize the best chemicals available to us. So that's ammonium perchlorates, aluminum, hydroxyl terminated polybutadiene, that's the fuel and also what binds everything together. It needs to be manufacturable. So in our case, we want it to be pourable and heat curable because it means we can decide when it solidifies and it's able to shape around more complex geometries. And it also needs to be able to meet the required flight dynamics. So our booster needs to be able to get our rocket moving and stable and fast. So that's where we're trying to achieve around a 15-to-1 thrust-to-weight ratio. And the sustainer doesn't really matter how it burns, but we want it to burn as long as possible. So, how do we do that? These are our formulas. So, I'm not going to say these are the most optimized formulas in the world, but we had to make compromises. So, our solid loading, so our first stage, or AST1, is 84% solids, and our second stage, AST2, is 78% solids. Both of those are not very great. The 78% solids especially. But what that does for us is that propellant burns real slow, and that propellant burns faster. Because you have more solids, they're able to conduct the heat faster. And so that's one way we regulate the burn rate. If you also notice, there's two different particle sizes for our ammonium perchlorate, which is our main oxidizer. And that is to improve pourability. But because it's bimodal, or two, it's not the best. And that was because we only had these two sizes available to us. If we wanted to go with a more finer particle size, we would have to mill it down ourselves, which is really not ideal, especially because we don't have any prior experience doing it. And then we have aluminum. This is an additive that allows our propellant to be much more energetic, as well as be a little more portable because it is that smaller size, only 5 microns. And then the oxamide, this is a burn rate suppressant. So this will cause your propellant to burn slower. It will also act as a little bit of a stabilizer. So it can stabilize out any of these burn instabilities. So our second stage propellant has 3% oxamide, and our first has 0.5%. So it's really not doing all that much in terms of slowing the burn on the first stage, but it is doing quite a bit on the second stage. And then the liquids are split between our ratios of the binder, which is the HTPB, and the curative, which actually sets it and gives us the desired hardness, cure time, and all those sorts of things. So, iteration process. We went through this a ton. And what I would say probably the most important tool, one of the most important tools we have, is a strand burner. This allows us to basically pressurize a chamber and simulate effects inside of a rocket motor. This requires very little setup work, and we can iterate extremely fast. So we can get a new formula, mix up a small batch, throw it in there, do 3 burns and get a good idea of how it burns. If it's terrible, we're like, okay, that doesn't work, try something else. And that can be done within days. And then, once we have something we like, we move towards characterization fires. So a little bit bigger motors, more propellant, they're able to better simulate what it would actually do in the motor and give us just better data, despite requiring much more resources. Then, after we have that data that we're happy with, we move to subscale motors. So we'll do something either a little bit longer or larger, kind of an intermediate between these small 54 millimeter in diameter motors that really simulates what the full motor will burn like. This brings us to experimental results. So our first stage propellant is that lower line, and our second stage propellant, the first stage propellant is that blue line, the second one is the orange line. This equation on the right models out what the burn rate will be, so it's pressure versus burn rate graph. So that white line is kind of our expected operating pressure. So at 500 psi, this will be burning at, the sustainer propellant will be burning at 0.097 inches per second, while the boosters will be burning at 0.168 inches per second.
Hi, so now to talk a little bit about the design of these motors in regards to the propellant geometries. So for those of you not familiar, solid rocket motors burning is all a function of burning surface area. Even though it may look like a tube, right, it is not a solid tube. There's usually a center perforation that gives the solid propellant surface area to burn. There's a lot of ways to control this surface area, and that is where you get into the design of the propellant grains. The most simple of this is just a straight cylinder. You can segment this cylinder and give a top and bottom face of surface to burn. That's what's called a base grain, and that is what is primarily used in the booster motor, which can be seen on the right side. Both of the sustainer and booster motors use what is called a finicil grain as well, which stands for fin on cylinder. And this is a way to increase the burning surface area while not increasing the length of the grain, and also allows you to achieve a monolithic geometry like we are using for the sustainer motor, as you can see on the left. The monolithic geometry, as the sustainer motor burns a lot longer, is able to reduce the thermal loading on the insulating liner as well as in the case itself. Because the sustainer motor has a very long cylinder, as the motor burns and you increase the diameter of the core, you increase the surface area, which means you will have what's called a progressive burn, where the starting pressure is low and the ending pressure is high. Pressure also correlates with thrust in this example. So this is optimized for the flight profile, where the more propellant on a sustainer motor that you can burn higher up in the atmosphere, the less losses to aerodynamic drag you have. One important note to mention here is you can see on both of these, the aft of the motor is finissil is in different places. The booster motor is in the aft, and for the sustainer motor, it is on the forward end of the motor. This is a way to control one of the more important parameters in the motor, which is called mass flux, or the amount of mass of gas that is leaving the motor per surface area. By having the finissil at the forward end of the sustainer motor, you're able to increase the mass flux, which usually you're trying to decrease it, but in our situation, we're trying to increase the mass flux, so you get what are called erosive effects on the startup of the motor. Because of how progressive the sustainer motor is, it is starting at a very low pressure, and when we want to test fire this motor, you can only externally stabilize the rocket for so long before it leaves the launch pad. So we want to make sure that the sustainer is able to, in its test flight, able to reach a passively stable airspeed before it leaves the launch tower. So we want to have an erosive startup that gives it a kick off the pad, essentially. For the booster motor, it follows a much more neutral burn profile, as in the pressure and thrust of the motor stays very neutral throughout the length of the burn. So having this finissil at the aft end of the motor controls our mass flux a little more and allows the simulated pressure curve to be much more close, will follow much more closely the actual observed through like imperial testing, the pressure curve of that. So here are some, this is a simulation of the burning of the motor. As you can see, it starts with burning inside out of this core, and you can see how the finissil grains progress over time, as well as just the standard Bates or cylindrical grains. One important thing to note is on the left-hand side of the screen, that is the booster motor, and on the right-hand side, that is the sustainer. The yellow line is the thrust of the motor versus time. I know you probably can't see numbers, but you can at least get the general idea of how they perform over time. Okay, so now I'll pass it off to Kate to talk about the mixing procedures.
All right, so you heard a lot about how our propellant was developed, and now we actually get into the formulation process. So to start off, we work in a lab at our PI. This requires a lot of safety procedures, and we are working very consistently with the Department of Environmental Health and Safety to ensure that all of our safety codes are being followed. We take our own care to write our standard operating procedures for chemical storage and handling, and we also use our own personal lab PPE to make sure that we're staying safe. So, to start off, we have to have procedures in place for doing these actual mixes, because they take a while. So one of the first things that we consider is our desired yield, which involves how much propellant are we making by mass. This also includes, as Rowan was saying before, what kind of geometry do we need? Because this involves making our own mandrels, which we either machine out of aluminum or we 3D print out of ASA. We also have to consider how much ingredient is needed for the day, because we also have to receive this from a separate storage facility on campus. Lastly, we consider how can we minimize waste in terms of this yield. So, some limitations we have in addition to yield that we have to consider while we're making these procedures. First thing is the order of ingredients. This is super crucial, as it is not only a safety concern, but also a concern of the outcome of our propellant as a whole. For starters, ammonium perchlorate and aluminum are a fuel and an oxidizer. We cannot have them interacting dry. That will cause danger. So what we do is we've taken very special care in order to keep them very separate for as long as possible until we can actually get them in with the liquids in our mixer. Additionally, we have had curing problems in the past, and we've discovered that our cure catalyst does need to be inputted with just pure liquids before solids has been inputted. Lastly, big consideration is time for the entire procedure because, again, it takes a while and some things need to happen in sequence. To start, we do have a cure catalyst. It helps our propellant cure faster, and our mixture will become too gummy to pour if we add it in too early. So we have to make sure that we're waiting the proper amount of time before we actually add it to ensure that we can cast properly. Some powders also take longer to fully wet out in our rheology calculations in the mixer. So we have to consider our mix times based off of that. It varies based on what sort of solids ingredient we're adding. Additionally, if the propellant is left to vibrate for too long, we risk settling the solids. We cast our propellant under vibration, and when we have a lot of liquids and a lot of solid particulates in our propellant all at once, if you are vibrating that whole mixture for too long, you risk having your solids kind of trickle all the way to the bottom and you get a resin-rich section at the top. So we have to account for our vibration time as a result of that, and we also have accounted for that in our casting design, where we allow for a small portion of our grain to be chopped off on top so that we can reduce that resin-rich section. So next I'll walk you through just a typical mix day for us. We have been very generously offered a mixer from the company called FlakTech, which Sawyer will get into in future slides. And this mixer has a maximum mix capacity of 1 kilogram. The Sustainer motor, our smaller of the two motors, requires 12 kilograms worth of batches. So we had to kind of do a lot of planning. And what we settled on was a cyclic mixing structure. So essentially we have 4 cycles of 3 batches. So you add all of your ingredients for your first 3 batches and you mix them in sequence, and then you cast them all in one. And then you do the same thing for your next 3 cycles. So on mix day, what you can expect is before mix day, what you can expect is to prep all of your casting hardware, make sure our casting caps and mandrels are all straightened out, make sure that we have everything all in order. We also have to cut and surface prep our casting tubes. Our casting tubes are made of XX grade phenolic, and that is a very tough composite material that we cannot just cut on the spot. We have to do a little bit of preparation for that. So that also has to happen in advance. Once we get on to actual mix day, we do a pre-mix with our liquids and then we pour them into our little FlakTech containers according to our appropriate batch size. Then we add in our ingredients one by one in that cyclic fashion that I mentioned before, and we mix the cycles in the FlakTech. Once everything is mixed, we store them at an appropriate ambient pouring temperature in our curing oven, just to kind of keep them at that temperature until all batches are ready to be poured, and then we pour them, as you can see in the top image, using a funnel into our casting tubes. We do this under vibration again, and then everything is left in our curing oven to cure at 60 C. Depending on the cure time of the propellant, because our propellants have slightly different cure times, that depends on when we can do our post-processing. Sometimes it's just later in the day, sometimes it's the next day. What post-processing involves is demolding, taking the mandrels out of the center of our now hardened grains. We trim off that resin-rich portion that I mentioned in the past, and we also do something that we call density scoring, which basically we account for all of the excess mass that is not propellant and the negative space for our coring mandrels, and we calculate the actual density of our propellant. This allows us to do an extra safety check before we do any sort of launching that ensures that our propellant is hard and solid all the way through. We don't want to have any extra voids in our propellant, as that would give us extra unpredictable surface area for burning that could have the potential to blow up our motor. So those are a big no-no. We try to avoid them at all costs. And yeah, that's basically what we do for processing and mixing.
All right, so mixing with the FlakTech. The FlakTech is a dual asymmetric centrifuge mixer. Fancy. So as you can see in that image in the top left, it rotates the cup as the whole machine rotates. This causes different viscosity fluids or particles to shear and actually mix the liquid. The mixer is also a vacuum mixer, which means that as it's mixing, the whole thing is under vacuum, so there's no air. So air cannot be added into the system, it's only taken out. And what's especially nice about this is it's constantly folding over the propellant as it mixes, so that it's exposing more surface to that vacuum and pulling the air out even better than if you were to just place it in and have it vacuumed. With the Flak Tech, we're able to have preset cycles. These are all customizable and can be repeated as many times as we want. We also can have up to 100 of them, 100 different ones. This allows us to have incredibly consistent procedures. So we know that if we put the same materials in, we will get the exact same result. Then we also have single batch containers. So we have, as you can see at the bottom right, all these batches lined up, so we can just take one container, put it in, do this first cycle, and then just we do the second one for the first cycle, and then say you go, then you back on the first one again, then you can do the second cycle, and so on. So roadblocks. What were the problems we actually ran into? There were some shipping delays at the start, so we had a bolt fall out, and it kind of threw an error, so we had to resolve that, but we sent it back, and everything was fixed, and that was fine. Then propellant processability. This was a huge issue for us, because we had never used a mixer like this before. And we found that by varying things like speed and the amount of time, it will drastically change how the propellant comes out. So you may not have caught it very early in the slides, in the formulation slides. You can see the container with kind of like a brick of propellant in it. That was some of our first formulations, as well as like mix cycles. And we kind of had the worst of both worlds in terms of having a pourable propellant and understanding how we need to mix our propellant to get it to be more pourable. Then, after that, we were like, okay, this can't stay like this. So we went back and we reformulated a bit. Then we took that and we mixed a bunch of different variations till we got something that was pretty good. And then we ran into some issues with a little bit of consistency. So we were kind of on the edge of something that was mixable versus kind of the actual mix procedure being correct. So sometimes we would get bad batches and sometimes we would get pretty good ones, and it was kind of that not understanding of this mix procedure. But we finally have it completely down, so every single batch comes out exactly the same. And then batch cycling and scalability, we can only do 1 kilogram at a time. It kind of sucks, but we've developed procedures around that to accommodate for that and get us be able to make these motors. Now I'm going to pass vehicle design off to Constant and Joe.
So now that we understand the propellant formulation process and how it's manufactured, fundamentally we need to understand how we can contain all the energy that's produced by these propellants to create a safe and reliable launch vehicle. And to do that, we're going to break every part down. So starting with the highest level, this is how the full stack will appear with the booster and sustainer stage. As stated previously, it's a 6 to a 4-inch reduction. And the two-stage design allows us to be much more efficient in the amount of propellant that we need to produce, which of course saves money and saves us a tremendous amount of time because once again we are producing all of these propellants in-house in our own lab. So starting with the first stage booster, it's a 6-inch outer diameter with the fins being constructed from carbon fiber cloth with an inner carbon fiber panel. We found this material selection to be efficient in 2 ways, one of which is, of course, it's very lightweight, so we can gain additional feet in our altitude, and it is also quite rigid, so aeroelastically it's quite efficient. And of course they also do have to be large for stability purposes. The actual case is made from the same aluminum that we've been using throughout the rocket, being 6061 aluminum. And on the interior, there are 2 layers of phenolic, one being a casting tube in which the actual propellant is poured, and a casing liner. And these 2 layers of phenolic help to protect the aluminum from the very high combustion temperatures, because aluminum is a soft metal with a relatively low melting point, so we need to ensure that it's able to contain this energy.
So for the part that actually couples the 2 stages together, we're using an aluminum structure with a slip-fit cone that essentially inserts into the exit cone of the second stage nozzle. And this gives it really good rigidity when it's under acceleration, because it's locking, it presses and locks the 2 parts together. So it's a 3-part design, so for ease of manufacturing while also maintaining rigidity. And it's held together by screws with a fiberglass coupler or fiberglass airframe that is bonded to the aluminum. And this also holds the parachute and recovery section for the booster. For the second stage sustainer, we're going with a 8-foot long rocket that is, as mentioned, 4 inches in outer diameter. And it essentially follows a sub-minimum diameter construction in that the motor case is the airframe as well. Typical rockets usually have an internal motor mount, but this is just inefficient for high-performance flights. And this thing is built to be rugged because it's supposed to endure a hypersonic flight, but also be cheap and reusable. And we follow a bolted fin design using 6061 aluminum fins with brackets that are bonded to the to the motor case, which allows us to get a lot of strength out of this. And you can see a wire diagram in the top image. You can see basically the guts of the rocket. And the second image from below that, you can see how the rocket is put together with the nose cone separating from the top of the second stage motor. And the third image, you can see a cross-section of the motor itself. And you can see the grains, the nozzle, which is optimally expanded for higher altitudes. And you can also see the recovery section, or the coupler at the top. And the bottom right image is kind of what makes this design special, is the head end igniter. There's no igniter from the top, through the bottom of the motor, which is what's typically used in high-powered rockets. This is ignited from the top with a special basket that holds an ignition pyrogen. So the top of essentially what spearheads through the atmosphere is a nose cone, and this also is built rugged and durable. It follows a 7:1 von Karman shape profile that's made out of fiberglass with a titanium tip due to the high temperatures that Joe mentioned in the dynamics slide. And you can see a common failure point with high-performance rockets with the nose tip is that it's not adequately retained, and and sometimes if the stresses are high enough, the tip just falls off the rocket. And that will end up with airflow entering inside the nose cone, and you end up with the rocket collapsing in on itself, which is not ideal. So our design, which is special, has a frustrum that essentially allows the tip to thread in and preload into the nose cone, and it becomes virtually impossible minus the thread, a steel threaded rod shearing from falling off. And the nose cone is what holds our electronics, because we're trying to be most optimized for volume and mass packing. And the sled is also structural in that it holds all of the recovery forces once it separates from the rocket. And you can see kind of how it's laid out. The black tube is where the main parachute is stored inside the rocket. It's called a chute cannon. The recovery team will get into that in a future slide. But yeah, that should be pass it on to show how it's actually built with John and Ellen.
Yeah, so thank you, Constantine. As engineers, we know that to design something is one thing, but to actually manufacture it is something completely different. And our team can attest to that. We've had to redesign parts over and over again, not only to make them manufacturable, but to optimize for weight and for cost. So this is our rocket. The exterior is made up of 3 separate materials. The nose cone tip is made up of titanium. It's the only part that's made up of titanium. The second material is aluminum. This is the body tubes for the sustainer and for the booster, and it's the sustainer fins and the interstage coupler. And then finally, what we manufacture in-house are the composites. This includes carbon fiber and fiberglass. And from left to right, this includes the booster fin assembly, which is made up of fiberglass and carbon fiber. It includes the booster recovery section, which is made up of fiberglass. This is a small tube where the parachute for the booster sits. And then finally, what I'm holding right here is the actual nose cone. This nose cone, although it looks simple, took us roughly half a year to get the manufacturing process down. And to talk more about this, as Constantine said, it's a 7-to-1 von Karman shape. And it probably doesn't look like it, but the shape is pretty complex. So we're going to go through how we actually manufacture this and the 2 different steps, which are the prep and the actual layup. So just to go, what is this actually made from? This is made up of 2 different types of fiberglass. The first type is 4-inch fiberglass sleeves, which you can see on the bottom left. It has the blue background. These sleeves basically can roll right over. It's very simple. And the second type of fiberglass we use is normal fiberglass cloth. Now, what's the reason behind this? Why do we use 2 separate types of fiberglass? And the main reason is because of the weave direction. When you use sleeves, although they're simpler, they have a weave direction of roughly 45 degrees, so like this, which you can also see on the bottom left. But when you use cloth, the weave direction, we can set it to whatever we want. So it's mainly straight. This matters because hopefully the force on the rocket will be directly vertical. And with weave and with the fiberglass cloth, we can actually set it so that the weave direction is exactly vertical. Finally, we use Cotronics Durlaco 4461 epoxy. This is the industry standard. It's a very expensive epoxy, but the reason for this is because of its high glass transition temperature. It's 500 degrees Fahrenheit, which is the highest you can get. So now I'm going to go through the 2 different types or stages that we take for this nose cone, which are the prep and the actual layup. So how do we, so to prep and make this nose cone, we have to make a mandrel. This mandrel you can see in the middle, it's made out of PLA and it's 3D printed. The mandrel itself is very long because the nose cone is very long. This nose cone is roughly 36 inches long. And if you don't know, it's really hard to get a 3D printer that can make an entire mandrel in one piece. So what we do is we separate it into 5 different parts. Then what we do is we thread them together and epoxy them together, and then we made a homemade sanding jig using a drill to make it as smooth as possible. Then we use a store-bought latex mold release device, and then we spray on mold release that we get online. Finally, the next step that we do for prep is the fiber processing. This includes cutting sleeves and also cutting gores. Gores are a specific shape. They are, if you were to take half of this shape and then lay it flat, and the way we manufacture this is by putting it into a laser cutter. So we have multiple laser cutters around campus, and we cut out, as you can see all the way to the right, these fiberglass gores. And then finally, the layup. So the layup we use is a sleeve gore method. The reason for this is because of concentricity. We want this to be as round as possible, and we found that if we alternate, it allows us to get the greatest wall thickness we can get. Finally, next thing we do is we weigh for the fiber ratio. This is basically the weight of the cloth itself over the entire weight of the nose cone. Research states that to get the strongest material, you want a roughly 64% fiber ratio. And then finally, we've been working through vacuum bagging. If you don't know, vacuum bagging composites, especially something that is round, is really difficult to do. But we've been experimenting with different types of bags and different types of procedures to get that right. After it's laid up, as you can see through this animation, it then goes into its gel phase, which the epoxy requires at 90 degrees Fahrenheit for 24 hours. Finally, we do a 250 degree cure phase in the oven, which you can see all the way to the right, at 8 hours to reach the 500 degree glass transition temperature of the epoxy. So we manufacture two other parts in-house. The next part is the booster recovery section. Again, this is where the parachutes are held inside of a rocket. We make this out of fiberglass, mainly because of the weight properties we can get from it. It's super light. So the actual procedure we follow is we do something called roll wrapping. Basically, you take a mandrel, 3D printed tube, and you roll over fiberglass cloth on top of it. And this creates a really concentric, strong final product. We use 9.5 ounce cloth made out of fiberglass, and we found that we can get tolerances plus or minus 10 thou. And then finally, again, we're using Cotronics 4461 for this as well. And then the final thing we manufacture in-house using composites are the actual booster fins. Now the reason why we're manufacturing this using composites are again because of its weight and also because we can remove it very easily. If you look on the bottom left, we use something called a fin can design. Basically what it is a tube that the fins are connected to. And again, the reason for this is because of portability. These fins are very large, so having to transport this from here all the way to Nevada, where we're eventually going to launch this rocket, is going to be really difficult. So the way we manufacture this is we create a tube, just like we were talking about before, where we use the roll wrap method. And then we water jet G10 fiberglass sheets and then we bevel them, and then attach them using a homemade custom 3D printed jig. And then we do a tip-to-tip carbon fiber layup. Basically what this is it's that middle photo where you just lay carbon fiber piece by piece, and you do multiple layers, and it creates a really strong, crazy isotropic final product. And then finally, another thing that took us a long time to get right was the actual vacuum bagging of the tip, of the fins themselves. You want to do this just so you can push all the layers together, and also to decrease the epoxy amount to increase your fiber ratio content. In the end, you get a stronger product. I'm now going to pass it on to Ella, who's going to talk about how we manufacture the rest of the rocket.
So most of this rocket is CNC manufactured. Most of the parts that we have designed are incredibly complex. Take, for example, the fins. The double wedge diamond airfoil is extremely hard to manufacture, especially on CNCs, because of how thin they are, just to reduce weight. So all of our aluminum components are made out of 6061 T6 aluminum, and we keep all of those tolerances plus or minus 3 thousandths of an inch. All of the parts are then bead blasted and then given generally an anodized coating. Either hard coat for some of the outer surface, which you can see here, and some of the inner surfaces are anodized just for better thermals. We also have our titanium nose cone that we've talked about before. This is made out of grade 5 titanium. We keep these to a tolerance of plus or minus 7 thousandths of an inch with just the machined finish. This is because titanium is incredibly hard to machine, and we need to be able to have this manufactured, and our friends over at HVCC are doing this for us. And to make sure that we can get this on time, a tolerance of 7 thousandths is pretty much required. For the actual nozzles themselves, we have the phenolic carriers. These insulate the case from the hot gases that are coming out from when we light the motors themselves. These are made out of CE phenolic with a tolerance of plus or minus 5 thousandths of an inch. Finally, we also have graphite nozzle inserts. These are made out of superfine isomolded graphite with a tolerance of plus or minus 5 thousandths. Next, I'll go over the manufacturing that we have done in-house. These are the characterization motor nozzles that we machined in-house in the JEC. This is just the CAD design drawing, which allows us to go and make these by hand. motors that I just talked about. We made 5 of them in order to characterize and test all of our propellants. To make these nozzles a lot stronger, we do something called, we harden them. In this, graphite is a very porous material because it is just a powder that is compressed together. To fill in those pores, we use a polyurethane that we vacuum in to pull out all of the air and replace all of that air with this polyurethane. Once we release it from the vacuum, we let it sit inside of the polyurethane for a couple of days before pulling out and letting it fully cure. Finally, I'll talk about the head-end ignition fabrication of our sustainer motor. This uses essentially 3 parts. We have the actual plug itself, which helps seal the hot gases from the chamber from the inside, so that way we can pass wires through to ignite the motor itself. As you can see, there's a couple holes inside with the green, and that is filled with a room temperature vulcanizing silicone, RTP silicone. What this allows us to do is create a really airtight seal around the wires that we have to pass through from the avionics to essentially light the motor using E-matches. The reason why there's essentially 3 different sizes of holes is that way that when the pressure pushes against that RTV, it essentially compresses itself against everything, which creates even better seal, just to help keep those hot gases away from the rest of the rocket. Next we have the basket itself, which holds the BKNO3, which is our igniter system, which are our igniters. This is a lot bigger, this is quite long, but it allows us to get the right pressures for ignition. Next, I'm going to hand it over to Trey for avionics and Taylor.
Thank you, Ella. So I'm going to switch gears here a little bit, and we're going to look a little bit more on the inside of the rocket and how we're going to safely recover this. So this is our avionics stack. It features 2 flight computers for redundant operation. Our primary flight computer being the Kate-3, which will control motor ignition and act as our primary means of detonating our black powder charges. These black powder charges are what release our parachutes during multiple states of flight. The black powder charges separate the rocket, allowing the chutes to release. And the Kate will attempt to do this at apogee, and Fluxus will do this a couple seconds after apogee. The reason we chose these flight computers, primarily the Kate, is because it's one of the only commercially available flight computers with no GPS altitude lockout. Essentially, all GPS chips on commercially available flight computers will lock out beyond a certain velocity or certain altitude. The Kate does not feature altitude lockout, which allows us to be certain we made it to space. Without a GPS chip, that has no altitude lockout, we cannot be certain that we made it to space. We would only be able to use accelerometer data, which is noisy and not entirely accurate. But as the Kate has no altitude lockout, we can see exactly our position during all states of flight below Mach 2, which apogee should be below Mach 2, hopefully. Yeah, and another thing about the Kate, it features a high-power 1-watt transmitter, which will allow us to receive telemetry downlink during the entire flight, which is useful for a couple things. First, knowing the state of the rockets, so we know whether we ignited our motor, and as well as how high we are, and our velocity both going up and going down. Hopefully, our velocity going down will be optimal, being not non-ballistic, but it'll also give us a little early warning sign if we are coming in a little hot. Going on to our backup flight computer, it serves a couple of different functions beyond just redundancy. It also controls our payload bay, which features redundant cameras. The Fluxus flight computer is able to monitor these camera systems and remotely start them. So we're going to move on a little bit to that actual payload system now, too. The payload system on this rocket is comprised of an aluminum heatsink with GoPro-style cameras. These GoPro-style cameras are stripped down and taken apart so they can be permanently bonded to this aluminum heatsink. We do that using thermal paste and epoxy so that they can dump all of their thermal energy they are creating into this heatsink. Otherwise, without this aluminum heatsink, we would only get around 5 minutes of recording time. These chips on these GoPros produce let's say, absurd amount of heat when they're recording, because our goal for this project is to record at 4K 120 and get some of the best footage of a space shot ever by any amateur team. That is one of our primary missions, and that is what this payload is designed to do. The hopes with the redundant cameras is even if one decides to, say, take a nap, we will have a backup system and still get footage. This footage is not directly downlinked, live streamed to the ground station, just due to the high bit rate. It's just not feasible or really possible at this current time, but it will be stored on micro SD cards and retrieved after the flight. In addition to these GoPros, we will have numerous on-pad cameras and video of the rocket's ascent, hopefully via drones and on the ground from where we're standing with generous donation from Lens Rental. I'm now going to hand this over to Greg Chen with Recovery, where she's going to talk a little bit more about how we actually deploy these parachutes.
Right. So, I'm sure we're all thinking. Forgot that. I'm sure we're all thinking, wow, it is a difficult and impressive challenge to build a rocket that goes up supersonic, hypersonic even. However, what's just as important and just as difficult is to ensure that it does not come down supersonic. Let's say our sustainer was coming down at what would be its terminal velocity without parachutes. That would be around transonic, and it hits the ground and its speed goes to 0. That is hundreds of thousands of joules of energy that must be absorbed into the structure, and that rocket would completely obliterate itself as well as any person or property in its place. And as a rocket team, safety is our utmost priority. So to look at the general kinetic energy formula, this will be our impact energy. And if our mass stays fixed, the only way to reduce this when it hits the ground is by reducing that speed. We are in fact doing that with parachutes, and our goal is to stay below 25 feet per second with our ground hit velocity. So both our booster and sustainer would each be equipped with 2 parachutes. That will be a drogue or a pilot parachute right at apogee, and then a main parachute that does most of that air braking. This is known as dual deploy in the rocketry hobby, and it is known to minimize drift. So we are, unlike typical dual deploy systems, however, which have the 2 parachutes come out of 2 different separation points, our goal is to have it come out of a single separation point in the rocket to reduce space. So that would look like this for our sustainer. That'll be separating at the nose cone. And as Trey mentioned earlier, this separation is done by having black powder charges, which are energetics, that when ignited by the flight computers, they will pressurize the recovery volume and separate our rocket. Now, if our rocket's made to separate, what's holding it together? So on the way up, we will be using, for each rocket, we will be using 4 440-sized nylon set screws to hold the airframes together at that separation point. And this was chosen to account for the atmospheric pressure difference between here and space, as to ensure that the rocket does not prematurely separate. However, at apogee, we have calculated the necessary black powder charges that will break the set screws using their shear stress and cross-sectional area, which is pictured there, and that will be enough to separate our rocket. And finally, one number that we really use to advise our selection of chutes is parachute opening shock. This is the most detrimental force in the whole entire sequence, and that is when the parachute fully inflates and the whole system experiences its major deceleration, and that drag force is distributed along the canopy. And if it's too high, the canopy could rip itself apart. So looking at this formula, we actually used a method that was used by the US Army, this opening shock calculator. It really comes down to the standard drag equation that you may have seen before, and a lot of that is just plug and chug, but I want you to take a look at one important variable. That's known as the opening shock factor. It's labeled as C sub K. And this can be calculated by looking at this graph of many data points of reefed parachutes, unreefed parachutes, ribbon parachutes, parafoils, and they graph something called the inverse mass ratio along their opening shock factor over there. And it follows this trend. And basically, in simple terms, the inverse mass ratio is the ratio between the volume of the air inside your canopy to the mass of your whole system. And you can see that as this increases, the parachute shock factor decreases. And this is how you can obtain that number to plug into your equation. So over there, we have marked the yellow and the green, the yellow being our booster and the green being our sustainer. And that is how we approximated our opening shock value. And you'll see this in the next slide. That number was approximated using those upper bounds that you have seen on the slide beforehand. So now on to the actual implementation. We'll start off with the booster. This will occur, so you can see with the two images here, the sequence of how the parachutes will come out. The booster apogee separation will occur at the booster's apogee. So imagine the sustainer has already lit itself, it's taken off, and this is a little bit after staging. We are going from a 36-inch diameter chute up to a 96-inch chute. And you could also see that that descent rate, 20 feet per second, is in fact below the 25 feet per second maximum. We could also see our opening shock, and that has a factor of safety of 1.7. And then for our harness choice, we have chosen a 40-foot braided Kevlar harness that is rated to take up to 5,300 pounds. Now, for this ejection system, how do we want two parachutes coming out of the same spot in the rocket to deploy at two separate times? Well, that drogue parachute will come out during initial separation. However, the main is protected in a Nomex blanket, and it will be kept in that folded configuration with zip ties. On each zip tie, you can see on this little cross section on the bottom here, we will be attaching something called cable cutters, or also known as cat claws. And this is also pyrotechnic activated with the black powder. And basically, when receiving the signal from the flight computer, it has a little piston, and it will basically cut those zip ties. And that takes away the constraint from the main parachute, allowing it to effectively catch at our desired altitude, which is 2,000 feet from the ground. And onto our sustainer. So our chute, it will go from 12 inches up to 60 inches. The drag coefficient also increases as well. We are hitting the ground at 23 feet per second, and it has a similar harness. And then for the ejection, so the main problem here, unlike the booster, is actually getting full black powder ignition in a vacuum. How do you do that? With a lot of high altitude flights, Rocketeers actually notice that their rocket does not pressurize and fully because not all the black powder gets ignited. And that's less due to the lack of oxygen as much as it is due to the lack of air pressure up there. When black powder gets ignited in a vacuum-like state, it tends to scatter. And those unignited particles kind of scatter out of the vicinity before heat even gets the chance to reach it. So we are solving this with what we call charge cannons. Those are those copper tubes that you see. And what they do is they have a crazy big length to diameter ratio. And as opposed to your usual charge wells or little charge pods, that long length to diameter ratio kind of confines the black powder initially, so it doesn't get the chance to escape before the heat from the gas of the previous black powder particles can reach it. And then as you can see, where is it? Oh, okay, whatever. Yeah. As you can see right here, this is where the main chute will be held. We are calling it a chute cannon. It will be printed out of PPACF, and it will basically, as we said, constrain the main chute before 2,000 feet. And at 2,000 feet, the black powder charges inside the chute cannon will pop open the cap that will be at the end of this. You can see that in the exploded view over there. And then the main chute is ready to come out and decelerate our rocket so it does not blow itself into smithereens. All right, I will be passing it on to Ella and Luke for testing.
Thank you. So we built our own custom 4-inch static fire test stand. This is made out of 10 series T-slot extrusion, otherwise known as 80/20. We use grade 30 chain to separate and hold stand down to the ground, especially during firing, as you can kind of see on the image to the right. Those are connected to ratchet straps, which kind of help extend out the reach of those ground ratchet straps to help hold the entire static test stand in place. We use chain because it is metal, and the rocket motor is constantly ejecting very hot gases and very hot materials. If any of that hot material lands on any of the ratchet straps, which are generally made out of nylon, they're just going to burn straight through that, and then those ratchet straps will snap or fail, which we really, really do not want when we have a rocket motor firing. To take the actual data on the thrust stand itself, we have one 10 kilonewton load cell and one 20 kilonewton load cell. We also have a 2500 psi pressure transducer, which allows us to measure the pressure and the force generated during each firing. To actually collect this data, we have designed what we call our data acquisition box. This allows us to collect the data from those sensors that I previously mentioned. We collect both of the load cell data at around 70 hertz or 70 samples per second. The pressure transducer data we sample at around 200 hertz or 200 samples per second. To do this, we use our own electronics, starting with the processor, which is an ESP32, specifically the Heltec V3 Wi-Fi kit. Then we have the two HX711 load cell amplifiers. These are needed because the actual voltages that are coming out of the load cell are quite small, and so you need to amplify that in order for the processor to be able to read that. Next, we have a SD card breakout. This allows us to store all of the data that we generate off of the RAM on the ESP32. Next, we also have a 5-volt regulator. This allows us to use a lot of different batteries in order to power our processor. To actually run all of this, we have our own code base, which is Arduino based, so C++. This allows us to have the capability to sense when the test starts and log all of our data. This also allows us to decouple our data logging, which allows us to log at those two different refresh rates. This is required because Arduinos are single core chips, which means they can only do one process at a time. So our code allows us to more easily log the data at the two different refresh rates. Our 4-inch test stand can only handle up to, as it's stated, a 4-inch diameter motor. Because our booster motor is 6 inches in diameter, however, we needed to make a much larger and much stronger static fire test stand. So we've designed this 6-inch what we call our 6-inch static fire test stand. This will allow us to test motors up to 8 inches in diameter. However, it will be used in our case for a 6-inch static fire. This is made out of 15 series T-slot extrusion, which is significantly stronger than the 10 series that was used previously. This also uses the same grade 30 chains and ratchet straps to hold it down onto the ground. Instead of having one 10 kilonewton load cell and a 20 kilonewton load cell, we just have two 20 kilonewton load cells because the motors that will be fired on this test stand are significantly larger with significantly more force. Again, we also have that 2500 psi pressure transducer.
So, a little bit of a switch from there. We have a hydrostatic test system. A rocket motor is essentially a pressure chamber where you're directing the flow out one direction to create thrust. So, when we're creating these pressure chambers, these motors, and working with machinists to actually make them, how do we verify that it's not going to burst during a test and something catastrophic could happen? What we do is we hydrostat test the system. This is where we pump water to a very high pressure into the actual motor casing and we close it off, and just to see if it's going to leak, if it's going to pop, if anything's going to happen. The reason why we use water is because it's an incompressible fluid. Sorry. So if it does pop, it doesn't store energy and explode. So you can see on your left, this is a rough diagram of it. So we have a hydrostatic pump, which is hand pumped, believe it or not. It takes about 100 pounds of hand force to get to 1,000 psi, and that pumps the water into the motor, which is sealed. And the motor also has a pressure transducer, which we use the DAC box, and we can monitor in real time from the gauge pressure and the actual pressure in the motor to make sure that the gauge isn't wrong or the pressure transducer is not wrong, and we go way past our safety factor we're trying to reach, and it pops. Next, moving on, so you heard Sawyer talk about strand burning earlier with propulsion. So how does this actually work? What's the testing procedure look like? So how strand burning works is we have a pressure chamber, and when we make propellant, we'll make hand batches before we make big batches in the machine to see how processable they are, how they look. And to test these, we do hand batches. We cast them in a 3D printed mold, and they look like rectangles. We take them out of that mold, and we measure their length. Then we dip them in an inhibitor, and then place them in our strand burner. A strand burner is a pressure chamber which is sealed, and we fill it with inert gas. And we fill it to inert gas during 3 different tests at 3 different pressures. So essentially and then we ignite the propellant, and we measure the burn rate by using a high-speed camera and counting the frames per second to how long we measured the propellant strand to be. And why do we do 3 different pressures? It's so we can predict how the propellant acts on a large scale. So you might have heard the term characterization thrown around. That's basically what it's doing. We're doing 3 different pressures. We're checking how it burns, what's the burn rate. So now we can model more complex geometries and scale the propellant. So on the top there is those 3 different data points with a fitting. Our R-squared is not the best on this one. I didn't grab the best example, so there is some uncertainty there. But historically, we found that strand burns with higher R-squareds are about 5% off actual characterization fires, which is very good when we're trying to iterate propellant very fast, having this test procedure. It saves us money, just like the hydrostat saves us money, because a case doesn't pop in the field, it might pop in the lab, and you actually can fix it really quick and iterate really fast so we can keep moving. That's one of our primary goals as tests. Static fire. So you can see, maybe you can't see, but these are both the same size test burner. Why does it look different? Well, the same characterization fire is similar to the strand burner. So you heard Ella talk about how we have nozzles, 3 different throat sizes, and we process them. Why do we have 3 different throat sizes on our characterization? Okay, the video's not playing again, but it's to do the same exact thing we do on the strand burner. So we take it in the lab, we do our small scale testing, and next we go to 54 millimeter testing in more of a realistic simulation of our actual grain geometry, right? So once we take this out into the field, why did those 2 videos look different? It's because the nozzle sizes were different. One was way overexpanded, where you saw that aluminum shooting out almost like a flow separation, and then on the right-hand side, you saw more of an optimal nozzle geometry, where we try to hit the same pressures we hit in the strand burn, and you can see how far off is this from our actual lab testing? How can we dial this in? How can we dial our mixing procedure in to actually get more realistic results in the field as we scale? So those tests, this is what the data looked like from the one you saw on the left and right. And you can see, why is there a big spike? That's called erosive burning, as Rowan talked about earlier, where when you have a large amount of gas at startup, it actually shears particles off the wall and creates a pressure spike. So when we take out these characterization motors into the field and we test them, we actually test for their erosive properties. That's something the strand burner really can't do. So by seeing how much of a pressure spike we could potentially get in a large scale propulsion system from just the small scale data, we can scale that roughly and even scale it more if we want to be extra safe, and we can create a motor that's designed to withstand something that needs a higher safety factor, that we know how erosive it is. So sometimes during our static fires, we actually create geometries that are more erosive than we're actually trying to do, to create more of a pressure spike to see roughly, how does that compare to the resting flat area in our propulsion system?
All right, I'm going to talk about a bit of the testing that we do outside of just propulsion. We did a tensile strength test on the avionics sled that was shown previously. We have these Instron machines on campus which allow us to pull the sled to see if we can actually handle some of the forces that it may experience during flight. On the left, you can see kind of that picture of the sled itself on the Instron machine. Unfortunately, this Instron machine can only handle up to 5 kilonewtons of force, which is around 1,000 pounds of force. So on the right, you can see the force versus displacement graph of the actual sled itself, and it didn't fail, which is really, really good. Next, I'm going to hand it off to Trey for acknowledgements.
Yeah, so it's safe to say we could not have done this without help. We're not on our own here. We received massive help from both RPI faculty and others. Starting off with RPI, we received guidance from various RPI faculty and support in terms of providing lab spaces and just helping us get this mission along its way. We would not be at this point without RPI. It's just plain and simple. They've supported us through the very beginning up until now, up until post-space shot. In addition to the RPI, we've also received guidance and support from industry professionals, people over at Anduril helping us with our propellant formula and mixing procedures, people over at FlakTech supporting us with the mixer and providing guidance on that, as well as people in the amateur rocketry community helping us gain certs, gain experience and knowledge from our first mix all the way up to level 3 certifications. In addition to this, we've received support from over 70 different members of our community, family, faculty, and various donors who have supported our funding campaign. This funding campaign has raised over $13,000, and we're at almost 70% of our goal. This is huge. This is one of the ways we make this space shot happen. We could not have afforded things such as the K3 flight computer without this funding campaign. This funding campaign has supported us along the way. We held one last year, and we're holding this one again this year to fund things such as the aluminum fins, like I mentioned, the flight computer, as well as all the different chemicals we need to make these motors. And then corporate sponsors. A year ago today, this would have been almost blank. And 1 year, we have gained dozens of sponsors, largely due to support from people in the community, as well as our success from IREC, the Intercollegiate Rocketry Competition last year. Some notable ones being Anduril supporting us financially, as well as providing mentorship. FlakTech providing our mixer, RPI providing both funding and mentorship, American Pacific providing the ammonium perchlorate we use for our propellants, Lens Rental providing camera systems, Hudson Valley providing machining, and numerous others who helped us get where we are today. And then something else we just started doing is offering merchandise. And this also helps fund not only our competition, but the space shot itself. And Noah's going to talk a little bit more about this.
Yeah, so we have merch. If you guys ever want to kind of represent the Ascendants, I don't think we've ever had publicly available clothing, but if you're interested, feel free to take a look at this link, and we'll get to you as soon as we can. This is just to kind of gauge the minimum order quantities. We're engineers, we're not manufacturers or clothes designers, so we got to figure all that kind of stuff out ahead of time. So moving forward, Elle and I, we're going to put the link back up. Elle and I are going to kind of go over the future work that is associated with this, and Elle will kind of lead us off with the short-term plans.
Yeah, so these are our short-term plans. We are planning to do full-scale motor static fire tests in the very, very near future. Once we have that data, the static fires, this will allow us to make our sustainer test flight, which will happen at IREC this year, which is held in Midland, Texas. This will allow us to fly our sustainer just by itself, just to gauge how it will do and get some more flight experience. Then we will have our first integrated test flight. This will happen between June 20th and June 22nd in the Black Rock Desert in Nevada. This will be our first chance to surpass the Kármán line and reach space. If this date doesn't work out for us, we have our second backup integrated test flight, which will happen between September 19th and September 21st of this year. This will also happen at Black Rock Desert in Nevada. If the first integrated test flight does go well, we will then use the second flight date to try to do it a second time. This would allow us to be one of the first teams to do 2 successful attempts in a very, very short amount of time.
So one of the biggest things that every engineer needs to consider when working on a project of this complexity is, what can I do better? The biggest part about engineering is iteration, and as you know, at our core, we are a propulsion team, and we believe that there's still many more steps to take with our propulsion systems before we reach industry standards. So first of all, both motors are not properly optimized. The AST1 is not perfected for efficiency. You can definitely increase your solids loading, and the more oxidizer and fuel that you stuff into lesser liquids, you get a higher C star as a result. Up to 88 is what we've seen in industry. As for the burn rate, currently, it's on the slower side, so the incorporation of catalysts such as red iron oxide, ferrocene, katazine, stuff like that can give us a bit higher in our burn rate. Additionally, I'm not going to get into too much detail about this, but you can also get into more exotic formulations. As for AST2, we initially designed this propellant because it's a center perforated grain to go as slow as possible. However, with a better understanding of slower burning propellants, you can actually optimize the geometry to get nearly perfect volume loading and essentially much greater efficiency, not by going slower, but by going faster. So the grain geometries that you've seen so far are center perforated. They have a large hole down the middle with some special deviations in their geometry. In this new iteration of AST2 would actually go the other way and be a faster burning propellant, where the propellant would burn as an end burning configuration. There's no center perforation, it doesn't burn outward, it burns upward, kind of like a firecracker. So if doing that, we would achieve much greater burn times, but the thermals would be a much greater consideration. So if you want to make it burn faster, wired end burners are the way to go, or a faster propellant. However, that's not relevant at this time. Now, what we can do with the airframe is increase the mass fraction. We're running very heavy on our materials. We're very reliant on aluminum, and with the case material, that takes up a lot of mass. Currently, our mass fraction is at 0.483. From what we've seen with industry standards, I think one off the top of my head, the Arcus, have a listed mass fraction of around 0.7. And as you know about mass fraction, that's essentially the mass of your propellant divided by the total mass of your rocket. To those that have taken any introductory spaceflight class, your delta V actually scales asymptotically to infinity as your mass fraction approaches 1. So getting into that sweet spot of a 0.7 around that can give us a much more efficient rocket with less propellant needed to be used. In terms of the actual construction, how we would accomplish that is the use of composites. Our casing, instead of being made of aluminum, it would be made out of carbon fiber in what's known as a composite overwrap pressure vessel design that you see quite a bit in industry. The picture on the right is one from our very good friend Thomas Buska that did a rocket in this sort of fashion. You can notice how much of it is carbon fiber. Lastly, when I first started this project, obviously the goal was to get to space, and there's many ways to proliferate this project once you're much more advanced with what you can do. And what I mentioned previously with our corkscrew and coning motion is the implementation of active controls. just recently for my final project, I developed an early model to essentially implement a control system in our sustainer. It's a model predictive control scheme, 9 degrees of freedom capability, and essentially you can mitigate any sorts of pitch roll coupling. I don't want to get too much into detail, but that includes waypoint optimizations. Let's leave it at that. As for what can Project Ascendant do after the space shot on the propulsion side of things, we can obviously look into liquid engines. We have plans in mind after this to make simple blowdown engines. To those of you that know the Mojave Sphinx, we'll probably dabble into that. May get into regenerative cooling. Maybe 10 years from now, we'll make RDREs. Who knows? Now, going kind of back, grounding ourselves, starting this project and seeing the presence of space in RPI, there's obviously a lot of potential. By doing a lot of space shots, showing that we can design a space shot in a very high launch cadence. Literally, we started this project 2 years ago with nothing. The space shot design itself didn't happen until late last year. So that kind of speaks a testament on our launch cadence if this were to be successful. What this potentially can go into is an RPI space program, and by extension inspire more universities around the country to get into space shots. The purpose of actually presenting this is to show that, hey, this kind of stuff is possible with a team of 11. You don't have to gatekeep this information. But before we can do any of that, we need a successful vehicle, which we hope that we summarize pretty well in our design. And with that being said, thank you all very much for coming. We'll take questions as they see fit.
We have yet to make our final decision as to whether we are 100% full sending this in June or whether we're going to push it off until September. It is basically hedging on a few of our machine parts arriving in time and the weather conditions of our launch, because a lot of things can get pushed back by factors we cannot control. So likelihood of launch in June, I would say, is probably 50 to 60% at this point, considering we still have some stuff that needs to actually arrive. As soon as that happens, probability will go way up, but we're just still waiting on a few things right now. Yeah, other than that, within our capabilities, we're very confident in our ability to get everything done that we can control in time.
Steven Spencer online asked, have you tested the recovery system in a chamber or for live flights? I'm going to let Gray take over for that.
Yeah, so recovery testing was something we really prioritized because Yeah, so we really prioritized testing recovery because you could have everything figured out on paper and in theory, but with our shoot cannon and charge cannon designs and all these, it's very iffy and up in the air. So we had our first recovery test flight in February up at a launch site called ERG, and it was successful. We tested both our first nose cone composite as well as the shoot cannon and charge cannon design, and that was successful. We are having our second fully assembled test flight tomorrow, and we will be including the Kate GPS, so it's really important that that one works, as well as our renewed design for sustainer recovery. Thank you.
Alternate, so.
Do you have it?
It's a question for either Joe or Constant. What are you doing to combat some of the potential of any heating effects on the fins? That's
So generally, when you're in the hypersonic regime, that's when we're going to experience most of the heating. It's generally proportional to 1 over the square root of the radius of your leading edge, like very, very approximately. So the smaller the radius, your heating can go through the roof. So we had to find the right sweet spot where we can have a sufficient radius where we won't severely damage the aluminum based off of the heat transfer and the aluminum's ability to radiate that heat out to its surroundings, either through the boundary layer or just through thermal radiation. But we also want to make sure that the shock wave remains relatively close or even attached to that leading edge, because the moment you have a substantial distance between your shock wave and the leading edge of the fin, your drag coefficient can ultimately even prevent successfully reaching space. We could be under by thousands of feet. So as long as we find that right balance with the leading edge, we can minimize the heating. The fins for the sustainer will also have a specialized coating that will ablate, it'll shed away and remove that heat that we could experience.
There was another question online, again by Steven Spencer. How do you determine that it is safe to ignite the sustainer? Is it angled to correct to go up or not go sideways?
Yeah, so I can talk a little bit about this. So the sustainer ignition is entirely controlled just by the Kate flight computer, and there's numerous staging logics that have to be met in order for it to light, because it could be catastrophic just for the state of the rocket and safety-wise if the sustainer lights at the wrong time or bad angle. So what he was getting at is we will only light the sustainer if it's within 10 degrees of vertical. There's additional staging logic related to velocity, so we need to make sure we're above a certain velocity but below another velocity. There's also altitude considerations. This sustainer should never light below 30,000 feet for any reason. So that's another consideration, because that means something went considerably wrong during the flight.
That's a similar question about upper stage ignition. What do you have in place in terms of physical lockouts to prevent upper stage ignitions with a head-end system like this before you have the whole stack vertical, for instance?
Yeah, so that's an extremely important consideration. It is extraordinarily dangerous to have an igniter installed in a rocket, because it means that you're essentially ready to launch. So that head and bolt that we were looking at earlier is only installed once we're on the pad and ready. That is the only point. In addition to that, there's numerous safety shunts, both in the attached to the bolt itself and the avionics section as well. So how it looks like when we're actually going and getting ready to launch is that bolt will be installed under shunt, so that what shunt means is the wires are twisted together so no rogue current can get in and ignite this E-match. Little bit, without going into the weeds too much, there's also safety shunts in the actual avionics, so when it's plugged into the avionics section, it is completely isolated from the flight computer itself. And only once it's vertical and we are weighed, those safety shunts are removed, both via magnetic switch and on the kit itself, there's internal switches that'll be removed.
Back there?
Yeah. So you mentioned that in future development goals, you'd like to look into liquid fuel rocket engine development and or CubeSat development. There's another club on campus, the Rensselaer Space Flight Society, that is doing both liquid fuel rocket engine development and CubeSat development as active projects right now. Have you reached out to them or talked to them at all to learn more about their project and their progress with it?
Yeah, I have actually. Sorry. Yeah, Spaceflight Works. They actually been in our lab to actually check they want our regulators and our gases. So we've been actually in a bit of contact with them, not so much as of recent, because we were busy with this, but seeing the kind of projects that they do, I think it's really cool. We need to have more of that space presence on campus. However, I think our position within the Ascendants is more putting it into a launch vehicle. Their engines are a lot more advanced, I'd say, than any of the liquids that we can make currently. Our goal is to put it in a rocket first. We're not really intended to go into CubeSats yet. At least that's not up to me, that's up to the future over here. But as for using it for any sort of CubeSat or any orbital project, I'm not too sure about that. We're just going to make it work in a rocket first, potentially.
To simplify that, we want to make one that we can actually fire, and maybe it's not the most efficient or complex, but it's something that can actually be fired and seen and iterated on and made better over time instead of coming out with something really complex.
You had a question?
Yeah, I actually have a couple, for a couple people. So I guess for the first one is the C factor safety for the interstage coupler, that's number one. Number two is how is the chemicals of the propellant chosen? Was it just industry standard that you went by? And number three is that you were talking about achieving lower grain for your propellant, and so that you had to do milling for the future, but you said you didn't have any prior experience, and so you didn't choose to do that. So what's the next steps going beyond that to achieve that lower grain? So there's three questions I have.
I can actually answer all three of those.
Go ahead.
So interstage coupler, the minimum factor of safety on that thing is 5. And that's accounting for a force even greater than what it should happen in flight. So we really have no concerns over whether if it's strong enough or not. And that was just done through Fusion 360's FEA solver. In terms of propellant composition, how we determined that. Ammonium perchlorate composite propellant is kind of an industry standard for propellants nowadays. It's what NASA uses, it's a lot of what the military uses, and it's because it's a combination of safety factors and performance. So ammonium perchlorate is is a very good oxidizer. It's also very easy to get, and you can get it in spherical forms. So that was kind of an easy decision because there's really not many other options that are good. There's ammonium nitrate, but it's nowhere near as energy dense, and it's a lot harder to get. And then you have like the aluminum. There are a ton of studies based where they would go through, like in the 1950s, like all the different metals and stuff like that to see what's the most energetic, and aluminum is by far the best option. And then, sorry, what was your third question?
My third question was, you said that you wanted to achieve lower grain, but you had to mill it down, but you didn't do it because of no experience. So how do you do that moving on to the next steps or for the next project that you're working on?
Yeah, so there are different milling methods we can look into. So we do have an option of either sticking with our spherical grains, which we don't really want to do. There are some suppliers that provide fine ground ammonium perchlorate, but it's very expensive. So we didn't really have the funds to be able to buy this enough to put that in our motors. And then in terms of the actual milling, there are ways you can do it, and I know of people who have done it, but we were working on kind of a shorter time frame, so we didn't want to have to stop and mess around with that and get it in a way that's consistent. In the future, there are machines that are able to mill it down in consistent, good sizes that are in safe ways, but that's also something that we're going to talk to industry professionals about before we even attempt on our own. Hope that answers your question.
Yeah, kind of what Sawyer was saying at the end. It is also a big safety factor. Our ammonium perchlorate is a flammable oxidizer, so before we even start trying to physically mill down our own oxidizer, we have to make sure that we're doing it in a safe way so it doesn't just blow up on us.
Everything we do is through our guys' environmental health and safety, and we have to give them a multiple-page standard operating procedure on anything that is even a little risky, all the way down to spraying mold release or spraying anything that's could be a flammable fuel. So a lot of procedure would need to be done to actually get to this next step next year.
Yeah.
Completely changing topics. You want to talk about one thing I noticed, nobody talked anything about ground support equipment for the actual space shuttle attempt. What's the pad look like?
Yeah, I can take that. So we have CAM radio towers that we got from one of our sponsors, and so that will create the base of the actual launch tower itself. And on top of that, we have more 80/20 rails, so these are 15/30 to a velocity that the fins can start having some of that passive control. This is all, and then there's a blast deflector plate, stuff like that. But essentially, it's just a really, really tall tower with a rail on it that the rocket follows.
Yeah, we're going to include it in the slides, but we don't have, it's 15 feet tall and we're assembling it inside. So it's really hard to get like a nice photo of it without taking it outside. So we just didn't include the photo of it.
Yeah, question back there.
Do you guys have beyond just getting the best footage from an amateur team, do you have additional goals for going to space? Do you have any plans for future publications, putting out your research?
So as it stands right now, we're currently trying to submit an extended abstract to the AIAA. Which conference is it?
I believe we're doing aviation.
The aviation
San Diego.
in San Diego, which is next year?
Yes.
Yep, in 2026. So we're going to submit an extended abstract and a paper to complement with that. So all of this is going to be published, if that's what you were asking specifically.
Yeah, kind of. I just want to know, what is the goal beyond just going to space? Is there something bigger there, or is it just we want to do something like school? And because either way, that's a good answer.
Yeah, no, of course. That's a great question. Okay, so in that respect, we want to make going to space more accessible, right? We just feel like, just seeing how quickly the group has grown in the past 2 years, that this kind of topic is something that I think a lot of college students should really get into. If we want to be a very space flight centered society, put it that way, if you want more people to get into space flight, if you want the market to go up for it, you need the students to be in that market in the first place. And giving them that confidence to build space vehicles, I think that's just gonna, if you want to look really long term, that kind of fulfills the initial objective of trying to get us to Mars, trying to get us off the Earth, and so on and so forth. So I hope that it's just our small contribution.
Yeah, and what's novel in our design, especially for the publication, is the affordability, which comes along with the accessibility, like Noah talked about. Having our two-stage design is very affordable, where we can do it under $25,000, whereas other schools who have done it in the past do one stage and it costs over $100,000, from what I've heard. So having accessible, affordable platform is very important for us and our goals. So any other questions?
Yeah, no.
So you mentioned right now that currently your casting of your propellants is only going into phenolic liners. Do you guys have any plans in the future to use spin casting for?
Yeah, so this is something that we have talked about extensively. Currently, casting as just into phenolic is somewhat easier just for the processing wise. We already have experience doing that. Spin casting is essentially makes, for those of you who don't know what spin casting is, it's essentially you have your, let's say your aluminum body tube. And what you do is you pour in some pourable liner material that will set over time, and what you do is you spin it up, and that centrifugal force will essentially adhere the liner into that liner material into a very thin but regular layer along the motor case itself. This essentially means that the motor case itself is single use because you are bonding what is the liner, which is inhibiting that heat, to the case. So your case becomes single use. And then you also have to then fill that in with the propellant somehow. So if you have any deviations in the thickness wall of your case, then you can't use normal casting tube methods, which means you have to cast the whole motor at once, which can be a little daunting. We thought about it, especially when we were thinking about doing that faster end burning propellant, that using a spin cast method is a lot easier to achieve much thicker liner walls, especially for a end burning grain where you don't really have to worry about having a core. You can just pour the propellant
probably take like 1 or 2 more questions, just because it's already here.
Do you have a question? I thought I saw your hand go up. No? Okay.
All right, I have a pile of questions, but I can ask them all later because I know you guys. So I think probably the biggest thing that I think would probably be generally useful to talk about. You talk about how you determine like go no go limits for things like weather or procedural stuff, where when you're deciding, okay, is 5 mile an hour, because you were talking about 5 mile an hour winds, how are we going to determine what's acceptable for that?
Yeah, for sure. So a lot of our launch day procedures and go-no-go procedures are based off of our simulations. We use not only OpenRocket, but open source simulation software called RASAero in order to semi-accurately, as accurately as we can, simulate our rocket and its behaviors. And in that, we can simulate a wind speed. So we do take our wind speed into account, and we simulate the wind speeds, and that does allow us to calculate our go-no-go. We haven't like set that hard limit yet because the procedure still in the works for that. It's more of a launch day thing, which we are actively working on. In addition to that, we also take like humidity and cloud cover into account. This is also like an RSO, range safety officer thing. Like if there's cloud cover, we're just not allowed to. Like straight up, that's just not allowed. So that's a clear no-go. Not even up to us. But in addition to that, we have checks from every subsystem. So we have checks from our propulsion. We'll be doing like inspections. We'll be loading it in. If anything looks even slightly wrong, we'll like take it out to check. And if everything is still good, then we'll load it in and we'll go. But like same with structures, we'll be doing like thorough observations of everything in advance, because the last thing we would have happen is to get this far, to plan this much, to work this hard, and then have like a silly little crack in the something. Like ruin our entire
Someone dropped a propellant crane.
Yeah, not have somebody drop a propellant crane.
So it transcends just launch day procedures. It's really assembly, go, no go, the integration on the field, go, no go, and then actual weather and on the pad, go, no go. And if, in our simulations, if it exits the parameter that we set, that we told the FAA that we wouldn't exit in our simulations, we're not gonna fly it during that wind speed. That's the answer.
Alrighty, I guess.
I think this is about as much time as we have. If you have any other questions, feel free
Please
to
come up and talk to us. Yeah, we just want to like formally wrap things up because it is after 3.
This video and this design review will be, we're live streaming, and it will be available on YouTube if you ever want to go back and look at it and review or just watch it again.
Or get the shirt.